So are you able, can you just confirm whether you are able to see like and hear
Yeah,
my voice
yes, sir.
clearly?
I can see you.
Yeah.
Yes, sir. I can see you and I can hear you.
Okay. Yeah. So yeah, good evening. My name is Parth Joshi. So I am basically pursuing my PhD at IIT Bombay,
Yes, sir.
and I like basically how I got into this is so I am basically a recipient of the Prime Minister's Research Fellowship, so which is like a prestigious fellowship for PhD research at IITs and other institutes. So I got an opportunity to interact with all of you for as a part of conducting these weekly sessions, which like consists of mainly problem solving related to the course content for this. So I have been doing this for the last 6 weeks, and now today we'll be discussing about seventh, like week seven contents. So basically, my background is like mechanical engineering. So I have
Mhm.
done my undergraduate degree in mechanical engineering from BITS Pilani Goa campus, and I did my master's in mechanical engineering with specialization in design
Mhm.
from IIT Bombay. And then I have worked in industry for around 4 years. So like in companies like Tata Motors, SKF Bearings, and Eaton. And then after that, I decided to pursue a full-time PhD at IIT Bombay. So I've been mostly working on areas of basically electric vehicles, and I have been using modeling and simulation quite a lot in my research work. So that's a brief introduction about myself. So yeah. So can you just quickly like give your introduction?
Yes, so I'm Twin Basu. I'm currently in my final year of BTech in Mechanical Engineering at Delhi Technological University.
Okay,
And meanwhile, I'm also actually working at IIT Delhi. So I'm part of Innovation Hub for Robotics program.
I see.
And I'm actually working on a double inverted pendulum. So I'm
Oh,
working on a lot of nonlinear control systems and I use Simulink for a lot of the simulations. So at
okay,
the same
okay.
time, I'm mine in automation design at DTU, so I thought this course would really help me
Right, right, right. Yeah, good. So yeah, so you must be already familiar with Simulink, right?
a little bit. Yes, actually, I just started doing the simulation work. So far, it's mostly been theoretical for me, so it's mathematics.
Right, right, right. Yeah, it's a good, like it's a very powerful tool. Like MATLAB and Simulink are like very powerful tools. Like they have a lot of, application specific toolboxes and many other like they have like one good thing about MATLAB is like they have a lot of examples. Documentation is very good. So and like you can if you have any any if you're looking for any questions or queries of how to do this or how to do that, you can just just might as well like Google it, and yeah, very likely you would find an answer. So yeah, so that's a good thing about MATLAB and Simulink. Yeah. So how are you using Simulink in your project?
So I basically it's you have one actuator and then you have two unactuated links. So I'm trying to control theta and theta dot, and I've modeled a motor. And what I'm trying to do right now is implementing torque control of a motor.
Right,
So right now, actually, I'm preparing the hardware itself. So a big problem I'm facing is so mostly motors they're made for controlling the voltage. Controlling the torque is not so intuitive. So
right,
for that, I have to modulate the current, and I'm currently just
right.
experimenting with all kinds of motor drivers, and I've been doing that for
Mm-hmm.
the last 1 2 months.
Right.
So now I'm towards the end of the whole part, and now I finally, I have a CAD model of the double inverted pendulum. I load that and doing a lot of things. I'm using PyBullet and other simulation softwares as well.
Okay. Okay.
So,
Yeah. Interesting. Yeah. Good. Good. Yes, and also I think Simulink also has some additional like hardware related support. Like in some cases, like you can actually build the model and
You
you
can actually
upload the
load the
code.
URDF. URDF you
Yeah,
can load into.
yeah, so you can upload the code into the hardware, like, especially Arduino based support is available for, Simulink. You can actually build the model in the Simulink environment and then upload the code. It
Mhm.
can generate the code for you. So yeah, it's a good way to, use that also. Yeah. Interesting. Yeah, glad to know. So actually, what I was planning to discuss today is, wanted to show you some demo examples related to how to use MATLAB and Simulink, both
Mhm.
MATLAB script as well as how to solve that same problem using Simulink.
Mhm.
Um, and we can actually discuss some things, like some points about the simulation setup, like all these things. If you might be already familiar, but yeah, so I don't know, other people may not be that much familiar, but yeah, so if you can also share your comments and whatever observations on whatever examples that um, we'll be discussing. So that's the
Yeah,
plan
sure.
for today.
Actually, I don't know too much about Simulink. I've mostly been in the theoretical part and hardware so far, so I'm trying to still get into the software side. That is why I
I see.
wanted to come for this meeting in particular, since Simulink discussion will be done.
Right, right. Yeah, then I think it would be a good starting point for you. I think we can, like, we'll be basically discussing some basic, mechanics based, some basic problems in mechanics you might have come across since, yeah, even, and like those problems we can actually try to solve using MATLAB Simulink. So either through script as well as through the Simulink environment. So yeah, I think you can get the idea of both the approaches. Like solving, it's basically about solving differential equations. So simulations in this particular uh, context for today, we are basically mostly discussing about how to solve different, differential equations using the different kind of solvers that are available in MATLAB Simulink. So MATLAB was like, when we are discussing about solving differential equations, so there will be like, different ways. So we need to solve the differential equation, we need to basically integrate the differential equations. And so there are various solvers in MATLAB which implement different schemes of integration basically. So some use like, what you might have studied. So it's like a implementation of what you generally would study in the course, like we take courses on numerical methods or numerical
In
analysis.
Rangakuta, like that.
Yeah, exactly. So there are some schemes where they implement Rangekutta methods. So for like nonlinear differential equations. Yeah, so so in most of the cases, like in real life, we will encounter problems where we will not be able to find an analytical solution as such.
Mhm.
So then we would resort to these numerical methods to solve that. And MATLAB has a lot of solvers to solve these differential equations. So you can explore that. So we'll be discussing like problems like, the simple pendulum. We can actually start with like the simple pendulum problem.
Mhm.
So like we we know that the simple pendulum is like the differential equation we generally uh, tend to linearize, like we find the analytical solutions for the simple pendulum, but there is an approximation that we generally consider, which is like the oscillations are like, small angle oscillations. So then with the linearized differential equation we can obviously find an analytical solution, but for for non-linear problems, like then we like in case of simple pendulum, we that's like, sorry, Yeah, so that's like an example, like it's like the simplest example that we can actually think of, which involves non-linear differential equation. So we can start our discussion with the simple pendulum example. So first we'll just look at the just we'll quickly go over the derivation of that differential equation, and then so you which you might be already familiar, but just to quickly brush up, we can actually just start looking at that. So let me just share my screen. So are you able to see my screen?
Yes, I can.
Okay, cool. Yeah, so what we will be discussing is about the simple pendulum example. So we will consider uh, like a simple pendulum with uh, you know let us say length L, and the bob has a mass small m, and let us say it makes an angle theta with the vertical. So now to derive the differential equation, what we generally do is like we draw the free body diagram, so and show the forces acting on the pendulum, so which is basically the so let us call the tension in the rod or string, whatever, for the pendulum as F, and let us write down the differential equation for the pendulum oscillations. So what we can do is like we can to derive the differential equation, so we can use either Newton's second law, or we can actually consider the moment about the pivot point, let us say O. So if we take the moment of these forces about this pivot O, then the force F actually passes through the pivot point. So then that will not cause any moment. And let us say L is the the length of the pendulum. So the moment of these forces about the pivot would be basically so mg into L sine theta, and since it's in a clockwise direction, we will put a minus sign. And the moment of inertia of the pendulum bob, so let us assume that it's a point mass, so the moment of inertia about the pivot will be just ml square, and yeah, so that will be theta double dot ml square theta double dot. So now if we derive the differential equation, it would be basically so in a simplified form it would be basically theta double dot plus g by L sine theta is equal to 0. So this is our usual differential equation. So then, if we generally go by the linearization kind of approach, so then we would basically do the approximation of like that sine theta is nearly equal to theta for small
Small
oscillations.
thing.
So then that
Mm,
becomes a linear second order differential equation. So for that, we know the analytical solution. So which is basically the omega square is g by L will be the natural frequency, and so theta is theta naught sine, sorry, sine omega t plus some whatever phase difference phi, depending on the initial conditions.
mm,
So this would be the analytical solution. But if we do not want to use this approximation and to solve this nonlinear differential equation, so then we can uh, resort to our numerical methods, like numerical integration based approaches to solve this differential equation, because there is no direct analytical solution to this, even
mm.
for this simple differential equation. So, so in that case, then we can model this system in MATLAB, like whatever in, let us say, if we want to use MATLAB to solve the differential equation, so then we can um model this differential equation. So for that, so let us move to MATLAB now. So I'll stop sharing this whiteboard now for now. So now, so I'm sharing my screen. So can you just confirm whether you are able to see my screen, which
Yes,
has,
sir. Yes, sir.
MATLAB?
Okay.
Yeah. So just for like the benefit of everyone, so let me just give a quick overview of what MATLAB is. So here, this is the MATLAB like general window when we open up MATLAB. So on the left hand side, you basically see the this is the current folder or working directory in which uh, so which contains all the files in the current folder in which we are working in. So this contains so this shows all the files which are contained in this folder. And if we want to change the for folder in which we want to work, so we can change it from this like you can browse it, like you give the path for the current folder from here. So I am considering MATLAB 2020A version. So depending on the version you would be using, things may change a little bit, but largely it would look something like this. So and on the right hand side, you see the workspace, which contains basically all the variables that you would be defining, and it shows basically the name of the variable, its value, and in some cases like when we have are working with arrays and also that will show the the size of that array and all that. So this is broadly the the about the window. And so if you want to clear things on the command window, you can use the command clc. And if you want to clear
Mm,
all the variables from the workspace, you can use the command clear all. So that will erase
mm.
all the variables from the workspace. So first we will start off with the simple pendulum, uh, the differential equation. So for that, what we have to do is like so there are several solvers for solving the differential equation. So let us first discuss about this very robust solver which uses the Rangakutta scheme of fourth and fifth order, like a combination of that. So if you want to read about any of these, anything about MATLAB, so if you type doc and then type the name of whatever that you want to read, so it will open up the documentation, MATLAB documentation. So here, in this case, we are looking at ODE45, which is a solver for non-stiff differential equations. This documentation gives us the details of what syntax we need to use. So what are the inputs and outputs that we need to the inputs that are needed. So and the expected outputs. So in this case, OD45 solver needs basically a function which contains the differential equation in a the state space formulation, basically the system of differential equations in this form. So y dash is equal to f of t comma y. um, you must have studied state space in this course. So
Yes, sir.
the system of differential equations we can uh, show it in represent it in the form of a state space, which is like a system of first order differential equations.
Mm.
So now let us go back to our whiteboard. So how to represent to see how to represent this differential equation in a state space form. Yeah. So are you able to see my screen again?
Yes. Yes.
Yeah. Yes. So now we have this differential equation here. So to represent it in state space form, we need to break it down. So it's a second order differential equation. So we need to break it down into two parts. So for that, what we can do is uh, we can define, let us say, state vector, let us say x, which is containing the variables, let us say theta and theta dot. So then, what is our we need to represent it in a state space form. So we need to represent x dot is some function of t comma x. So this is our state space form that in which we want to represent this differential equation. So for that, so let us write our first equation. So the first element in our array x1, so it is theta, and the second element is theta dot, so
Mm.
which is equal to x1
Excellent.
dot, right?
Mm.
And x2 dot will be theta double dot, which is minus g by l sine theta, which is minus g by L sine x1. So this is the so we need to provide the state vector x dot, like a function which gives us the description of how x dot is related to the state variables and time.
Mm.
So we need to write a function to represent this state vector derivative of x dot is equal to f of t comma x. So the system of differential equations has to be given to MATLAB as a function. So we need to write a function. So in MATLAB script, so this is our function. So I have named it as simple pendulum differential equation, and the inputs are basically t comma y. So y contains the the variables theta and theta dot. So here, so g is basically the acceleration due to gravity, which has been defined
So are
here.
you
And
writing something right now? I cannot see any change in the screen.
oh, sorry. Yeah, sorry, I forgot to. Yeah, I actually, sorry. Are you able to see my screen now?
No, I can't. So.
Okay. Yeah. So let me. Yeah. So I was basically talking about this simple pendulum differential equation. So you need to in MATLAB script we need to go to new script or new function. So I have written this using a function. So when we want to write a new function, so this gives us a template. So the function needs basically the function name and its input arguments and what are the output arguments, and this is the general syntax that we need to follow. uh, Now here I've already written the MATLAB code for that. So here uh, we have defined the two parameters, like, yeah, someone wanted to join. Okay.
No, so it was me. I accidentally cut the meat.
Okay. Yeah, so basically there are two parameters here, G and L. Uh, so the state space in the state space form. So like so what we are basically looking at is y dot in the state space form. So what we had discussed is that y1 dot is equal to y2, and y2 dot is basically theta double dot which is equal to minus g by l sine theta, and which is minus g by l sine y of 1. So here I have written y, but you can use any, like, and you can also write it as x or y or whatever, like, so you can also write it as x dot. So x, you can also name it as x. So just to be consistent with our derivation. So this code actually shows the function, like, which gives us the state space representation of the governing differential equation for the simple pendulum.
Hmm.
So then we need to uh, call this function in the ODE45. We need to pass this function to the ODE45 solver, and then the other two arguments which are needed as an input which are basically the basically the initial condition. So the initial condition here is that we displace the pendulum by some initial angle, let us say 30 degrees, and then we basically just use this initial condition and integrate the differential equation over a time span. So T span here is the which shows the start time and end time of the for integration of the differential equation. So the solution that we get is basically in the form of data points of time and the corresponding values of the theta angle and theta dot. So these are the outputs of this OD45 function here. So there will be two variables created in the name of t and y. So t will contain basically the time and y will contain the values of the state variables, which are basically theta and theta dot over here. So it will be a set of two column vectors. So y will be a set of two column vectors which will contain the values of theta and theta dot for the corresponding time. So let us try to run this script. So for that, here you have a run button over here. So once we press run, we get the output over here, which is uh, here in it's like basically in the it contains two subplots, one which describes the angle theta with respect to time, and this is theta dot with respect to time. So so this is the general output. So any questions till now?
No, sir, it's clear.
Yeah. So now if we want to actually see how this solution actually changes, whether how it compares with our usual analytical solution, what we can do is we can also plot, create a, see. So let us, for example, add the analytical solution over here. Um, so here, because based on the initial conditions, our like we are just displacing the pendulum by some initial angle and leaving it. So the analytical solution will be of this form, right? So theta as a function of time will be basically theta naught into cos omega t, right? So where omega so where omega is basically square root of g by l, right?
Yes.
Right. Now just to avoid any conflict with whatever MATLAB may have some inbuilt um, you know some inbuilt variable which is defined as omega or whatever. So let us write it as omg. So let us define an additional array for the analytical solution, which is contains an array of time uh, with a time space with time interval of zero point 0.1. So for every 0.1 second we will create the corresponding data point for the um, theta value, and the theta dot will be basically, so if we differentiate theta naught cos omega t, so what will be the expression for when we differentiate it with respect to time? So it will be, so omega into theta naught into sine omega into omega t. So these will be the two quantities that we will get for the the given, like, the time interval that we are considering.
Mm.
So does that make sense?
Yes, sir.
Yeah. So now if we want to compare how this compares with the analytical solution, so let us plot these the output t comma y, so colon comma 1 here. It means that we are extracting the first column out of the y. So y is basically a column vector. So if we go to the workspace here, so we know that here y is a column vector, like a array, a matrix with 177 rows and 2 columns. So the first column represents the theta angle and the second column represents theta dot. So here, so let us superimpose this uh, analytical solution plot. So let us call as theta A, call it as theta A and TA. So TA is the corresponding time and theta dot A as the analytical solution. So when we say hold on, it will basically uh, allow us to superimpose this other plot onto the axis. And if we now rerun this, we can see that, so the blue curve is the the using the
Numerical.
numerical solution, and the red one is the analytical solution. So what you can observe here is the solution for is accurate. The analytical solution is accurate for up to, let us say, first 3-4 seconds or so, but later on it seems to be deviating here, because in the analytical solution you can observe is that the time period is actually for each oscillation is the same, but the as per the numerical solution the time period seems to increase as we increase the time. Now if we actually want to see how the solution behaves over a larger time interval, let us change the time span to 30 seconds and try to rerun. So then you can see that the deviation actually increases even further.
Yes.
Yeah, so you can observe that, right? So um, so this was actually for an initial angle of 30 degrees, which is not
Mm.
that big an angle as such, but still we can see that there is a considerable amount of deviation from the analytical solution. Now let us change the initial angle to 10 degrees. So let us change theta naught to 10 degree. So and let us try to rerun. So now you can see that the analytical solution is like very close, right? So you can actually, in case like in other problems where you can explore this approach, you can, wherever you know the analytical solution or approximated analytical solution, and then you can compare it with the numerical solution in this way. So this was a demo example, so where we consider simple pendulum as the system. So was that interesting? Something different for you?
Mm, yes, sir.
Yeah,
So I understood. Yes.
yeah. Now similarly we can uh, so so I also wanted to discuss how to solve this same problem using Simulink. Uh, so shall we discuss that?
Yes, sir.
Yeah. So here, so when we go to the main MATLAB window, here you have a button called Simulink. So this will uh, directly give like open up Simulink. So or alternatively, you can also type Simulink on the command window, and that can also basically open up Simulink for you. So it will show the status as starting when it is starting Simulink. So it will open up this Simulink startup page. Now again, depending on the version that you are referring to, you can see that there are some changes, etc. So to create a new blank model, so you can just start from here, create model. So this is the blank model window, and this contains like the button over here for the library browser. So if you click on this, you can see the library or Simulink library here, which contains all the different toolboxes. So now depending on what you have installed, when you install MATLAB, so you get the options of installing different toolboxes. So depending on whatever you have selected while installing, so you will see the uh, different toolboxes that so you have. So to check which toolboxes you have already, so you can type in the command one window as ver. So that will show you the MATLAB version and also the toolboxes that you have installed, its version, and so all these details you will see. uh, so yeah, moving on to the our basic like model. So here so you will see the in the Simulink you will see like different blocks which you can explore for different applications, like so you have the basic Simulink blocks for continuous discrete systems, etc. And again, the application specific toolboxes over here, you can see it from the library browser. Now here we want to create a model of the simple pendulum. So for that we will use the uh, so let us first try to solve the linearized differential equation theta double dot is minus g by l theta, or we can also try to solve the non-linear version also from here. So now in Simulink, what we will be doing is that we will be integrating. So let me pause this screen sharing for the moment and go to the whiteboard again. So now what we will do here is we will create a block diagram to represent this differential equation. So what we will be doing is, so let us say we have this signal which contains the theta double, which is theta double dot. So what we need to do to get to solve this, what we need to do, we need to integrate it twice, right? Is that correct?
Yes, yes.
So so in terms of Laplace, in the Laplace domain, if we consider, so then the Laplace transform of of basically the integration integrator, so that is 1 by s. So we
Mm,
need to do this integration operation twice,
mm,
right? So
yes.
so if we integrate once, so then this will be theta dot, and if we integrate twice, this will be theta. So what we are going to, so how we are going to use this signal is we will do the operation of sine of this. So this will be our operation, and then we will use a, we will be multiplying it by minus g by L. So as per the differential equation, minus g by L sine theta is equal to theta double dot. So then this creates our theta double dot signal, like it defines our signal value, and
Mm.
this is the block diagram representation we are looking at for the
Mm.
Simulink. So in the Simulink environment, we will be able to, uh,
So afterwards, when it gets multiplied by G by L,
yeah,
then it goes back to this theta double dot, or is there a sink or something where this value will be stored and we can visualize it?
sorry, I didn't get your question. Can you repeat?
So you multiply by sine and you multiply by minus G by L. So you get ultimately minus G by L sine theta, which is what we know is theta double dot.
Correct.
So then this value will go where? It goes back as a loop, or does it go into a sink for visualizing some scope or
Yes.
something?
Yeah. Yes. We need to. Yeah, sorry for. Just hold on for a moment. Yes. So it does actually go into a sync. Like, so you can use like a scope, or you can store this value in the workspace. So you can do various things, like, so there is no source directly as such in this, because it's like a free vibration, right? So there is no source for this particular thing. So what is the, so in this case, this system, like, we give the initial conditions. So let us say we displace the pendulum by some angle and leave it. So it is in the
Mm.
form of potential energy, and once we leave
Mm.
it, so that's like the energy exchange continues, like in from potential to kinetic and all, etc. So it's free vibrations, right? So then there is no source here. It's in the form of initial conditions that we provide. So that gives us the starting point to solve the differential equation. So in the integrator, we will provide the initial conditions for each, let us say, for each integration.
Mm.
And yeah, so does that answer your question?
Yes, I can understand. Yeah.
Right. So let us now move to Simulink now. Yeah. So now let us go to our library browser. So let us put this integrator block into our Simulink model. So now to add this block to the Simulink model, so there are like various ways to do that. Either you can just drag and drop, or you can you know right click on the Simulink block here, add block
Mm.
to model, whatever the name is. So
Mm.
it's untitled here, and you can use the mouse to drag it and position it anywhere.
Right.
So now let us save our model and name it as simple pendulum. Now to connect these two blocks, what we can do is just from the left mouse button to use the left mouse button to drag a connection and place it into the input. So let us consider that this like the input to this integrator is theta double dot, so the output of this is theta dot. So our initial condition of theta dot is 0, and our initial condition for the theta is theta naught. So what we can do is either we can provide the initial condition as some numerical value over here, or if we provide the variable name over here, it can actually pick up that variable from the workspace. So here the initial condition is theta naught. So this is how we can give the initial condition to the integrator. So when we double click on it, so this contains the parameters. So we will be using all the default things, just put the initial condition here. Now the next part is creating sine theta. So here we will go to math operations tab in the Simulink library browser, and we will use the the common type of functions kind of block. So here here you have a trigonometric function block. So then you can add this block by right clicking. So this will add the sine. So since we want sine, we can just directly use the sine function. So you can also, it also has other functions which we can use. So you can explore that. So now we will basically perform the sine operation on this. So this will give us sine theta, and then we need to multiply it by g by l. So for that, to multiply it by g by l, so we have like two options. So we can simply add a gain. So you can either use the gain block, and if by double clicking on this, you can provide the gain as minus g by l. Since we have already defined these variables in the base workspace, so it will be able to pick up these values from there. Since so if we uh, do not have these variables defined in the workspace, we need to create a MATLAB script which initializes these parameters basically. So here, which is like L, G, theta naught, and all those things. And so yeah, that's it. So we have defined what is theta double dot. Now we just need to connect it to this integrator, and yeah, we are done. So now, so this will give us the theta value. So now if we want to convert this theta, so it will be in radians. So we need to, if we want to convert it into degrees, and for visualizing the output, we can convert this from radians to degrees by multiplying by 180 by pi. So in MATLAB, so you can use the word pi. So it has the inbuilt value of pi over there. So 180 by pi will convert it into degrees, and then we can use a scope. So now what we can, there is another way in MATLAB, like especially the newer versions, to add a block to the Simulink. So what you can do is, like, you can just double click anywhere on the screen and type. So you will see a magnifying glass appearing, and then so if you type the name of the block that you want, so so it will show the list of the blocks which match that description that you type. So I want to use, let us say, a scope. So then this is the way you can insert scope directly if you know the name, or otherwise you can navigate it using the usual way of, go to the sinks tab, and then so you have different ways so of different sync options. So you can also use a scope, and excuse me, And so if you want to log this variable to the workspace, so then you can use this sim out block to workspace. So what you need to do is create a branch and provide this as an input to this block. And here you need to provide the variable name by which it will be logged to the workspace. So let us say we give this variable name, and we can save it either in the form of array or structure with time or time series. So let us, we can save it for the time being as like time series. So time series means that it will create a structure which contains the time values for the simulation as well as the values of that variable. So it will store the time along with the variable value. So let us say OK. And if we also want to uh, store the value of theta dot, so we can add another instance of this block. And here we will, so after the first integration, we will get theta dot. So here we have to pick up this signal and let us call it as theta dot underscore t. And let us also store this as time series. If you also want to store the time values of the simulation time value, so when we will run the Simulink model, it will run the model over a certain time interval starting from 0 up to, so here we can provide the stop time. So here it is by default, let us say 10 seconds. And yeah, so we can simulate it for, let us say, 30 seconds.
Mhm.
And yeah, and if you want to store the time values, like simulation time values separately, we can use the source blocks. Go to the source blocks and you
Yeah.
will see a clock kind of a block. So you can add this block. So it will provide the output the current simulation time. And then this has the option of decimation. So what decimation means is that it will store the excuse me, it will store the variable values for every 10 time steps if the decimation is 10. So if our time step is, let us say, every 1 second, so then it will start at 0, then after 10 steps it will store like after time t 10 seconds and so on. So like that. So it will so if we pick up decimation as 1, then it will provide the output as at every time step. And then if you want to store this simulation time to another workspace variable, so then you can go to again sinks and add a, sorry, add a block. And let us name it as time. Now if we are already we are storing time, so then we might as well store it as an array, since time series contains the simulation time. So if we are storing a time variable separately, then we can also convert this into an array form, or we can also stick to time series. So depending on our memory availability and all those constraints and all those, you can decide whether you want to store it as a time series or the array format. So is that clear? So any
Yes,
questions? Any questions
yes.
on right? Okay. So now we are ready to run the model now. So now to run the model, what we need to do is here you can see something called as variable step auto. So if you click on that, so you will see that the solver name is like variable step auto. So if you click on this gear type of symbol, so then you will go to the solver settings. So here you can actually select what type of solver that you want. So the default one is like, let us say, variable step, and we allow, let us say, the MATLAB to automatically choose the solver depending on, so it will analyze like what kind of system that we have modeled and choose the solver accordingly. So if you go to this, expand this, so then you can see the solver details like maximum step size and minimum step size, etc. So to understand what is the meaning of all these things, so you can actually read the documentation to, so I will not be doing a deep dive into all these things, but let us say let us say to start with, we use the default options and see what is the output. So let us go to the run button and try to run the model. So it will first compile the model, and if there is no error, it will run the model, and we can see the output in the scope. So we can see here the output in the scope. So it actually doesn't seem to be that good. So you can see that the output doesn't seem to be realistic. It's like it never
Mhm.
is like this way. So it's a continuous system. It will not, this is like a jagged, it's not a smooth curve. So now let us go to our solver settings again. So if you hover over this right corner, so you will see auto. So what you will see that it has selected the solver named OD45, and it has selected the maximum step size as zero point 0.6, right? So now if we want to improve the so what it does, this algorithm, it generally does is that it starts with a coarse solution, and then it tries to refine it depending on, let us say, what is the gradient. So if the gradient increases, then it will use a smaller time step. So it can adaptively change the time step. So like you can here, you can choose the adaptive or non-adaptive, whatever method, like based on your requirements. So it's a simple problem here, so we can probably go with non-adaptive for now. So our earlier step size, like max step size, was zero point 0.6. So now let us try reducing the max step size and see whether it refines our solution. And let's try to rerun it. Yeah, so we can see that like the curve is more smooth, like the output is much more smooth as compared to the earlier one. Now you can also, like, consider refining the maximum step size further. So if we select, let us say 0.05 and rerun, so you will see that it has improved further, and it shows the uh, much more smooth curve as such. And it seems that the solution like is very close to the sinusoidal kind of a behavior that we were expecting. So now if we want to just cross check whether any if we want to again go to the documentation for any block, so you can go to double click on the block and say help, so it will open the documentation for that particular block. So it will give us the details of this particular and so here we are considering the angle in radians, and so by multiplying it by 180 by pi, we are converted into degrees. So that's about the way we can use Simulink here to solve this problem. So any questions?
No, it's clear.
Okay. Yeah. So similarly, we can now uh, let us move to another problem. So we know our usual spring mass damper system. So and we are already familiar with the, let us say, the differential equation for that kind of a system. So now let us return to our whiteboard now. Okay. So let us look at the how to use the like MATLAB Simulink to solve the spring mass damper kind of problem. So we know that the usual differential equation of a spring mass damper kind of a problem. So it is mx double dot plus cx dot plus kx is equal to, let us say, some force F that is acting for forced vibrations,
Hmm.
right? So now to give us this as a input to MATLAB, so if we want to use, let us say, MATLAB script to solve this, so then we need to provide it in a state space form. So let us choose our state vector as x1 and x2. So let us define x1 as x itself, and x2 is, let us say, x dot. So now, so if you want to break down this second order differential equation into uh, a set of two first order differential equations, so then what we can do is, so we know that x2 dot will be x double dot. So then we can rearrange these terms and write it in this form as, so x double dot will be minus c by m x dot minus k by m x plus f by m, right?
Hmm.
Then so basically x2 dot will be x double dot. So then we can rewrite this in terms of the state variable form as minus c by m x2 minus k by m x1 plus f by m. And our second equation will be x1 dot is equal to x2. So do you agree? So x1 dot is x dot, which is equal to x2. So that completes our definition of in terms of state space form. So now we can uh, look at the let us move to Simulink, move to MATLAB for implementing this state space form. So here, so similarly, like the pendulum case, we need to write a function which provides the uh, derivative of the state variables x dot as a function of uh, time and the state variables itself. So x dot as a function of x and time. So that here we will define the parameters of mass, stiffness, and damping, and let us say the force, external force that will be acting. So let us consider that there is a sinusoidal force uh, which has, let us say, an amplitude of 1, which is acting on this system. Or for that matter, for the time being, let us ignore the force, and let us consider the uh, just the general differential equation. So x, just we as we discussed, so x dot will be, so x1 dot, which will contain x1 dot and x2 dot. So it's a column vector which contains x1 dot and x2 dot. So the first row will be x2, x1 dot is x2, and the second row will, which is x2 dot, which is x double dot, which is our differential equation, like the right hand side of that differential equation, which is this minus c by m x2 minus k by m x1 plus f naught by m sine 2 pi ft. So here let us consider that there is a sinusoidal force, external force, that is acting on this spring mass damper. So this is the way to represent this in a state space form. So the input to this function is time and the state vector x, and the output is x dot. Now we move to the MATLAB script where we will be using this function. So our initial conditions are, let us say we displace the mass over here with point 0.1 by point 0.1 meters, let us say, and x dot 0, which is initial velocity, is 0. So y0 is contains the column vector of the initial conditions. T span gives us the time span, like this T start and the start time and end time, and we pass this to the function OD45. So we have to pass this function spring mass damper differential equation, the T span and the initial conditions, and the output will be basically time and the vector y, which will contain the which will be a column vector which contains the values of x and x dot. So any questions, any doubts on this?
Oh, so that's clear.
Yeah. Now we are create like these lines of code are basically to plot this the output simulation output in terms of figures.
Mm.
So here this is like subplot which creates like divides the plotting area into two, like, two parts. So depending on the inputs that you give to the subplot, so you can create like a tiled kind of a representation, or one on top of another, depending on. So this first input is the number of rows and this is number of columns. So and this is the number that is assigned to that subplot. So if you have uh, let us say if you do 2 comma 2, then this will have like four tiles. So then you have to number each one as 1 2 3 4. So here we are just considering two subplots, which first one contains the values of the plot for x and the next one for x dot. Now so these are the inputs that we consider, and then we can just now consider like running this MATLAB script. So this
Mm.
shows the output of the displacement with respect to time and the velocity with respect to time. So if you observe this, the nature from the nature, what you can say about the nature of the system, what kind of damping we have?
Uh, what kind of damping?
Yeah. So we have viscous damping, right? So like so
Oh,
depending
okay.
on,
Hi. It's,
so what kind of damping like do we have? So is it whether it is under damped, over damped, or critically damped?
uh, ultimately, the displacement goes to zero speed, and this is the same. Not sure, sir. Not sure.
Yeah, so here it is called as under damped because the it oscillates. The mass is going through some oscillations, but the
Uh-huh.
oscillations at during each the amplitude of the oscillations goes on decreasing exponentially.
Mm.
So that is called as under damped. So you have three regimes, right? Like three depending on the value of the damping, viscous damping.
Right.
So you have like under damped or over damped or critically damped.
Mm.
So like if we change the damping value here, let us say we here C was selected as 0.5, let us change it to 1
Uh-huh.
and try to rerun the script again. We can see that so if you compare here, the oscillations are dying out in lesser amount of time,
Mm-hmm.
right? So the damping has increased, and it will. reduce the time required for the oscillations to die out.
Mhm.
Then again,
Yeah,
if
but
you
so just by looking at the graphs, can we tell whether it's underdamped or critical or over?
yes, so the qualitative nature itself, you can, you know, so the nature of the graph itself will be very different. Like for overdamped or critically damped. So now
Mm.
to make out whether it is critically damped or overdamped may not be that easy. For that, you
Mm-hmm.
have to look at the specific damping constant value. But
Yes,
for
sir.
overdamped or critically damped systems, so there will be no oscillations at all. So
Okay.
we'll see. So if we go on trying out, like let us try to increase the damping values. So now we tried 1. Now let us try 5. So now you see that there are hardly any
Right.
oscillations now.
Mm.
So now let us reduce the time span to, instead of, it's much more clearer now,
Mm.
or even 5 seconds would be enough probably. Yeah. So this is for the damping value of 5. So if we go on again increasing the damping value to 10, let us say 10, and try to run it again. So you can see that the number of cycles through which it goes are going on decreasing and decreasing. But let
Mm.
us
Yes.
say there is like just like hardly one cycle of oscillation and it settles down to almost zero. Now if we select the value of 20, so if C is equal to 20, that is called as critically damped. So why 20 here? Because uh, the value of where C square is equal to 4k into m. So when C square is equal to 4 into m into k, which is 4 into 1 into 100, which is 400. And C, when C square is 400 or C is equal to 20. So that is the value of critically damped, critical damping value. Now let us try to run with that. So now if you observe, there is actually no oscillation
Oh, yes, sir.
and it just directly goes to 0. So if you kind of look at it more closely, so if you want to kind of zoom into the the plot further, you can actually pick up the time scale and use the magnifying glass tool to look at the plots more closely. But yeah, so you can see that there is no oscillation, so it is called as critically damped. And if we increase the damping value further, let us say we now go to 30, then there will be no oscillation, but the system will respond even more slowly. Like it will, so if you compare like our previous plot and this plot, here it settles down to the the steady state value of 0 within 1 second, and here it actually takes slightly longer for it to settle down. It will settle down to the steady state value of 0 itself. And even in this case, like even in the underdamped cases, it will eventually settle down to 0, but it will take longer. So as we go on increasing the damping value, it will take lesser time to settle down to 0. Now let us try another example of, let us try to increase the damping even further. So you will see that the time required to for it to settle down to the steady state values again slightly increased. so so you can see that the critical damping case is the one in which it takes the least amount of time to settle down to its steady state value. So when we design systems where we want to avoid, let us say, let us say in case of robotic manipulators, etc., uh, where we want to you know let us say if you want to move the arm, uh, let us say in a factory or anything like that. So if you visualize that, so robot which picks up things and places it somewhere, there we would like to have, avoid the oscillations as much as possible. Or even in case of, let us say, if you consider the simple examples of, let us say you might have come across doors which have a piston cylinder kind of an arrangement for automatically closing. So once you open the door and leave it, so it will automatically close the door, right? So it has a mechanism along with a piston cylinder arrangement, which is essentially a damper. So there you will never see it, if you leave the door, it never goes through any oscillations, right? You must have
Hmm.
observed. So those are examples of critically damped or over damped kind of systems where the damping is so much that there are no oscillations and it will just gradually go very smoothly to the steady state position of zero. So make sense?
Yes.
Yeah. So this is how you can use MATLAB script to uh, simulate this behavior. Now we can again try to solve this same example using Simulink. So for that, let us create a new uh, model. Sorry. So again, now we let us again try to go back to our whiteboard now, and so we had this kind of like this differential equation that we had. Now what we want to do is, so we have the x double dot as our let us say signal. So then our x double dot has to be integrated twice to get the displacement x. So one integration will give x and another integration will give x dot, and another integration will give x. Now what we know from our differential equation is that, so we have to multiply this by minus k by m into x, and then we also need to add minus c by mx dot. So we need to take the signal,
Hmm.
so minus c by m into x dot.
Hmm.
And if we have any external force, we also need to add that. So let us say, so that in case here would be, let us say, a source. So So we will basically add these three things together. So minus k by m x1, minus c by m x2, and f by m. So this will be added together, and this will give our x double dot. So this will be our block diagram in this case. So does that make sense?
Yes.
Yeah. So this is how we can create the block diagram in Simulink using this. So let us try to do that in Simulink now. So these will be our two integrators.
Mm.
Then yeah. So now here I have given the gain value as minus k by m, but now you can see that there is a red uh, highlight, or like Simulink highlights it as some red, and it shows the error as unrecognized functions or variables. So we have not defined these variables in the workspace here. So we will have to create a MATLAB script to define these variables. So we'll define it later. So let us first finish creating the blocks first. So minus c by m will be the gain value for x dot. So let us call it as x naught as the initial condition, and x dot 0 as the another, like the second initial condition. Now to add these signals together, what we need to do is go to math operations and select the block named add.
Mm.
So then you can, so for the time being, let us consider free vibrations. So then we'll neglect the external force for now.
Mm.
So that will be minus k by m x and minus c by m x dot. So that will become x double dot. So this we will go here, and then now what we need to do is create all these variables in the workspace. Let us say x naught is whatever 0.1, and x dot 0 is our initial velocity, k is some, let us say 100, c is let us say 0.1, mass is 1, let us say, and let us name it as spring mass damper init. And if we run the script, that will create these variables in the workspace. So you will see that So if you run these in the workspace, you will see these variables. Now, as we had discussed earlier, so let us create the sync blocks. So let us say scope, and let us store the velocity and displacement outputs. So this will be velocity. Let us call it as x dot. Let us store it in the form of array, and here we will have the value of displacement x. And now here we can see that this still shows the red kind of a highlight. So for that, what you can do is you can say in go to the modeling tab and say update model. What it will do is it will compile the model and show whether there is any error. And here it found these values of k by m and c by m in the workspace. So now it has removed that red highlight. So you can do this like to kind of debug the model, like, so when you are building it step by step, so you can use this feature to debug that. So now if you want to visualize both, uh, let us say both displacement and velocity, so then you can go into the scope and select the number of input ports as 2. So then it has created another input port. So so the second input will be velocity. Excuse me. So that completes our Simulink model now, and then we can now try to run this model, say for 30 seconds. Now with the default solver and step size options, let us just try to run the model first and see what its output is.
Hmm.
Yeah. So here this shows the two figures like in a superimposed kind of form. So now to visualize it into different subplots, so you can auto fit the contents here and see. So now you can see that the general output seems to be okay, but it's like still not a smooth curve as such. So then we might want to look at the step size. So again, it has picked up the solver of OD45 automatically, and the maximum step size has been picked up as zero point 0.6. So let us try to change that. Let us say 0.01. Now you can see that the output is much more smooth. So this was our output for the when the damping value was zero point 0.1. Now let us change that damping value to 1 and see how the output of the Simulink model changes. Now if we have not made any changes to the model, we can also run the model from the scope also. The scope also has a run button, so we can just do run over here, and yeah, you can see immediately that the output now has changed. Now the oscillations take lesser time to die out because our damping value has increased. Now let us increase it to 10. and and let us change the stop time to 10 seconds only. So we can see that the damping has increased. Now if you go to 20 and again try to rerun the model, so you will see the critically damped output where there is no oscillation. It's the same thing that we saw just now. So you can see the same kind of results as we saw earlier with the MATLAB script, though the Simulink model also provides the same results to us. So now with the damping value of 30, so again you see the overdamped kind of a behavior. So this is how you can use the Simulink as well as MATLAB script approaches. So you can also try to change the solver if you want, like if you want to use, let us say, a fixed step solver, and if you want to, like, let us say, leave the solver selection and step size as auto, and then try to rerun this model. Now you can see that the results are not quite satisfactory, uh, because the differential equation is non-linear and it has selected the step size of zero point 0.2. So we might want to refine the values. So let us start with the damping value of 1 and change the let us change the fixed step size to, let us say, 0.01. Okay, and then rerun this model. We can see
Hmm.
that we are getting the desired expected, whatever the nature that we are, so like the overdamped, so underdamped behavior, what we are expecting. Now if we change the damping value to 10 and try to rerun, so then again it shows the expected behavior. So we basically need to refine the step size, so like if we go on refining the step size, let us say instead of 0.01 we select, let us say, 0.005 or whatever, then we will reach a point where the behavior of the solution does not change much. So then there is no point in decreasing the type, as we go on decreasing the time step, it will refine our results hopefully. And but if we go on decreasing the time step further, and if the nature of the solution, like, it does not change, then we have basically it's called as convergence, right? So we converge to our whatever expected solution, and further decrease in the refining the time step will just increase the computation time. So then we need to select the depending on the computational, the memory. So as we go on refining the time step, it will also increase our memory requirement because we have to store a large number of values. So we have to select the time step wisely based on all these aspects, like how what is our memory constraint, and yeah, what is good enough basically, so that we need to think about. So I hope this gives you some good idea of the using MATLAB Simulink as well as the script, uh, right? Makes sense?
Yes, sir.
Yeah. Now let us look at a different kind of an example. which you might have come across in like your basic mechanics in school days, what we call as generally like a projectile motion. So it means is be like when we throw a projectile or some object into air and allow it, if it is thrown at, if we let us say throw a ball at from the ground and with some angle with respect to the horizontal. So based on the usual simple mechanics, kinematics, that we already know the uh, simple kinematic equations for that kind of problem. Yeah, excuse me. So yeah, so we already know from kinematics like how to solve those equations, but now if we want to simulate the behavior of that simple projectile thrown into air in a MATLAB simulating based environment. So what I mean to say is that, like, let us say if we have a coordinate system, let us say x, y, and if we are standing at the origin of this coordinate system and if we throw like let us say a ball with the initial velocity v, and or v naught, what is, for example, which is at so the inclination of that velocity vector is at theta with respect to the horizontal. Then the on like if we are throwing it into air, and if for simplicity, what will be the force acting on that mass? Let us say it is just a ball of mass m, neglecting, let us say, the air resistance or and whatever, its weight will be the only force acting on it, right? So the acceleration in y direction, so y double dot is equal to minus g, and the acceleration in x direction is 0, right? So these are the two differential equations that we get for this simple system of a projectile which is thrown into air. Now if we want to represent this differential equation in a state space form, so then let us consider a state vector of x1, x2, x3, x4. So what we need to do, what we as in the state space form, we need to write it as x dot is equal to function of x and time. So let us call x1 as our x, like the position, like the x coordinate of that point mass, and x2, let us call it as x dot x3, let us call it as our y, and x4 as y dot. So these will be our four state variable definitions. So in terms of the state space form, now x1 dot is x2, x2 dot which is x double dot, which is 0, and x3 dot is x3 dot is y dot, which is x4, and x4 dot, which is y double dot, which is equal to minus g. So these are the equations of in terms of state space form. And now we need to create a function to to represent these variables in a state space form. So now let us go to uh, MATLAB and see how to simulate this example in a using MATLAB script using our ODE45 solver. So here we in this script, what we have done is that we have defined our initial conditions of x0 and y0 is our initial coordinates of the projectile, which is, let us say, the origin. V naught is the initial velocity, and theta naught is the angle of projection of the projectile. So initial velocity is, let us say, 30 degree at oriented at 30-degree angle, and then uh, we basically create our vector which contains our initial the coordinates and x naught, y naught, and x naught, x dot and y dot, like the initial velocity. So the initial velocity in x direction is v naught cos theta naught, and in y direction the initial velocity will be v naught sin theta naught. So this is what is shown over is basically uh, we define the y naught array in this form, which contains the initial conditions. Then we give the time span, and there is also a parameter which is called as refine, which is given to the options for the solver. And then in this we also have one interesting thing which is called as event function. So when we are throwing the projectile and so it will initially go to some maximum height, and then it will again fall under the influence of gravity and hit the ground, right? So then,
Mhm.
so if we want to detect the uh, the time at which the ball, let us say, if the ball hits the ground, for that we need to create an event function, so to detect the event. So for that we need to create another function, which is like here we are calling it as bounce event function. So let us open that. So the syntax for that is this which is shown here. So we want to basically detect the time instant. So when the the solution it is integrating the differential equation. So what it will do is it will keep on solving the differential equation, and in this case it will be like it will keep on integrating even though the y value goes from it starts from 0, it reaches a maximum value and again goes down, and it will keep on integrating till the value of y also goes to negative. uh, Now if we are throwing it from the ground, then it will bounce back, bounce back up to the ground. So then the y value cannot go beyond 0, right? So it has to So we need to halt the integration when the y value reaches 0. So in the state vector, the y of 3 contains the value of y coordinate of that projectile. So what the time instant at which the y value reaches 0, it will stop the integration. So it will solve only up to that point when till the value y reaches 0. So this function is used to detect this event. So the event here is defined by this parameter position, which is the value which we want to be 0, which is y of 3. So when we said say is terminal is equal to 1, which means that we want to halt the integration. And the another parameter which is called as direction. So when the solver is working, so it some algorithms actually move like have both the capability of moving forward as well as backward in time. So they have some adaptive course correction kind of things inbuilt. So let us leave it to 0, which is like it can be approached from either direction. So that's about that function. So we pass this event function to the structure called as options. So this options consists of the structure where we want to customize some of the things which we want to pass to the solver. So one thing is basically the uh, events part, and the other is refine part. So which is like a parameter which provides us how much refinement of the solution that we want in the algorithm. So it's like specific to the algorithm, and you can read the documentation to know more about that. So we'll not go into the details of that. So then what we are interested here, so once we solve that, it will give us the values of t and y. So the y vector will contain now 4 columns. So first column will be x, coordinate of the projectile, then x dot, which is the velocity in x direction for the projectile. Third will be the y coordinate, and fourth will be the y dot, which is the velocity in y direction. So this will be the how the solution is. And now to plot the trajectory of the projectile, we will be interested only in the x and y coordinates. So we extract the first and the third column of the solution here, and we will plot that. So let us try to run the script. So from here you can see that this is the we launch the projectile over here, and then it goes to the maximum height of around 5, and then reaches the ground here at about 35 seconds. So the initial velocity is 20. So now if we change the the angle, um, then you will see the time of integration has changed, and the initial angle of the launching the projectile has also changed. So this is how you can use this uh, you know numerical solution method to solve the projectile motion kind of problem. So if we don't, now let us see how the importance of this particular event detection. So let us consider the case in which we don't pass this option of the function. So let us comment out that part and see how the solution looks like. So you can see that the solution actually starts from 0, and then it keeps on integrating for negative values of y, which we are not interested in. So it either the ball will just bounce off the ground and do more such bounces, or it will just go and stick into the ground, fall onto the ground, and that's it. So it will not go on, like it will not get embedded further into the ground, right? So then this, so we need to cut off this integration for the point beyond which y values are negative. So that's how you can, uh, in certain problems you can use this feature of event detection. uh, so let us say if we want to actually analyze the bouncing ball kind of a motion, so then for that we can extend this thing further. So here we are stopping like the integration at y equal to when y reaches 0. You can extend the same problem further, and uh, so here I have again created another example to solve this bouncing ball problem. So what we do is here we basically detect this event in the same way as we saw in the projectile motion. We are let us say looking at the problem where we just vertically throw the ball upwards, not let us say in the form of a projectile, and we want to see the height at which it reaches, and then it will come back and bounce, like hit the ground and again bounce back. So with each like bouncing event, so we know from the the general mechanics of impact. So the collision can be either elastic or inelastic. So in an elastic collision, so there will be no energy loss. So it will bounce back with the same velocity. So the velocity direction will change and the magnitude will remain the same for an elastic collision. But in reality, the collisions are never elastic. So then there is a certain coefficient of restitution. So the coefficient of restitution is like let us say will increase, will uh, model the kinetic energy lost in every collision. So here let us say we consider the coefficient of restitution to be let us say zero point 0.9 or so. So what we do is, so here I'll not explain the code in a lot of detail, but what we essentially do is we run this we again write the differential equation for the bouncing ball, which is that the like for an object which is freely falling under gravity. So that's the simple state space representation of that. So you can create this function for that, and then what we do is we pass this again the event function where we detect the position at which the y value is reaching 0. So the uh, event function will detect that time, so it will provide us the time of that event and the number of instances for which this event it came out to be true. So this condition came out to be true. So this will so here this, so you can actually look at the documentation further to understand this syntax more. So t, e and ye are the times at which the event occurs and the number of instances at which the event occurs, and the t and y are the basically the solution values. So the integration stops, or the algorithm stops integration at the point where the event condition reaches true. Now what we are doing here is, so we start with the ball thrown in air, then we solve it from the point of launching, then it reaches its maximum height and comes back to the ground, and we detect the time at which it comes back to the ground. We stop the integration and now create a new initial condition. So we update the position and initial velocity. So it changes the direction but the magnitude is also reduced by the coefficient of restitution. Let us say we consider it as zero point 0.9 in this case. So the solution value of the for the velocity at the end of the this solution. So for the end time, so the time and instant at which the integration ends, so the end value of that velocity vector here, that we store here, and update the initial condition, and again run it in a loop until, so let us say here we are using a for loop for let us say 10 instances. So for 10 times, let us say the ball, if it is bouncing, so it will find out the values of the height at which the ball reaches for every instance of the bounce. So that's what we are essentially doing in this particular code. And in this here we are plotting the figure of the values of the uh, the height at which it reaches for at each time instant. So let us try to run the script. So yeah, so
Hmm.
we can see here that the ball starts from zero, height of 0, reaches a maximum height again here, bounces back, but reaches a lesser maximum height, and so on. So like you can see that the height progressively goes on decreasing with every bounce.
Right.
So this is how you can use this feature of event detection in your problems where you want, uh, even in case of a pendulum, let us say it is hitting a boundary wall or something, then that you can also create this kind of an event function to detect this. So I hope, so I have tried to show you some basic examples of like simple mechanics problems in which you can use MATLAB and Simulink, and I hope this demonstration was helpful. So any questions, comments on the contents of the session?
Yes, it was good, sir. I understood everything.
Sure. So that's all that I had from my side for today. So I hope this demo helps you to get a, it serves you as a good starting point for using Simulink and MATLAB, etc.
Hmm.
So yeah,
Sure, sir.
yeah. So I
Yes,
think we
sir. I
can.
want to ask, will there be a hold out session so that students can ask about any particular topic that they want to before the exam is held?
Yeah, so there will be a session just before the exam. I think it will be on 16th of April. Yeah, so
Okay,
it will
okay.
be, I think, on 16th of
Exam is
April.
on the 5th of May, right?
I'm sorry.
Exam is on the 5th of May, right? The main exam.
Yeah, I think so. So I think the course is ending on 18th, right?
18th,
I think,
right?
I
Or 17th.
guess, yeah, I think it's ending on
It'll
18th or
be on
something.
16th, 16th, sir, I think.
15th itself.
Uh, yes, sir.
Yeah, so whatever. Like I think so there will be some like a doubt solving session before that, but it will be like a 1 hour session. So today we had a 2 hour slot. So
Yes, sir.
yeah, so before
Because
exam.
actually, I had some doubts in making bond graphs,
Okay,
the bond system models of hydraulic, pneumatic, and thermal systems. So I want
okay.
to, yes,
Yeah. So what you can do is you can also go through some of the recordings of the earlier sessions that we had, so from week 2, I think. So I think
okay, sir. Are they available on NPTEL itself or somewhere
yes,
else?
yes. So you will, so today's problem solving session, what we had, so you will also
Hmm.
get the recording of that, for that in the, like, it will be stored somewhere in NPTEL, so they'll provide you a link to that.
Okay,
Uh,
okay.
yeah,
Okay, sir. Sure.
yeah.
Okay, I'll go
So
through that.
yeah, sure. Yeah. Thanks. Yeah,
Okay,
thanks
sir.
for
Thank you
joining
very
the
much.
session. Yeah.
Yes, sir. Thank you.
Yeah.
Good
Yeah.
night.
Okay. Good night. Bye.